So if you want to measure intelligence, you need to rigorously define what intelligence is, which in itself, it's a very challenging problem. I think intelligence is essentially the efficiency with which you turn experience into generalizable programs. So what that means is it's the efficiency with which you turn a sampling of experience space into the ability to process a larger chunk of experience space.
Measuring intelligence in humans is difficult enough. Chollet here is trying to come up with a measure in machines, and that's a pretty daunting task. And although I don't agree with him on some of what he says and proposes and whether or not that's a good thing, I believe that the paper is pretty fun and the formalism at least holds in my view, and the ARC challenge is to me the most interesting part, because even though I don't think it's going to get us anywhere to AI, it's a fun challenge and it's a nice deviation from standard machine learning and standard Kaggle challenges.
Intelligence emerges from the interaction between a brain, a body, like embodied intelligence, and an environment.
Welcome back to the Machine Learning Street Talk YouTube channel and podcast. Today is Francois Chollet. Francois is a huge inspiration for me personally, and Yannic and Connor and I have all covered his Measure of Intelligence paper on our respective YouTube channels. And now it's time for us to do a deep dive into some of the ideas that Francois Chollet has. Chollet is one of the most credible critics of deep learning. He argues that at best, deep learning algorithms are just interpolating between the input space, that all they do is learn a geometric morphing from X to Y and only work given a sufficiently dense sampling of X to Y. There is no extrapolation, there is no extreme generalization, and given a few examples, it's impossible for deep learning algorithms to generalize in the way that we generalize. He would go on to argue in a further sense that deep learning algorithms learn shortcuts. They learn surface shortcuts, and they don't learn the kind of rules that we would learn in respect of the same task. There have been some incredible successes with deep learning recently, and essentially we've been throwing more and more data, more and more compute, more and more architecture, and these models are incredible, but we shouldn't make the mistake of thinking that they are reasoning. This is Chollet's argument. What these models are doing at best is the imitation of reasoning. They are taking shortcuts. And it's so easy to take shortcuts when you have these highly parametric models that are learning a geometric morphing in a continuous space. There are so many shortcuts that these models can take. Chollet pointed out that these deep neural networks perform a series of geometric transformations, mapping data from one manifold into another manifold, successively. Of course, assuming that there exists a continuous learnable transformation from X to Y. In order for that to work, Chollet points out that you need to have a dense sampling of X to Y. So you can think of deep learning models as being kind of like computer programs, but the inverse is not true. Deep learning models cannot represent most computer programs. The reason for that is the corresponding geometric transformation may just be too complicated, or there might not be enough data available.
That in the future, we're going to have machine learning models that look much more like computer programs, like the sort of programs that you might be familiar with.
Chollet is arguing for a complete change in direction. He's advocating strongly for program synthesis, some kind of a meta-learning algorithm which would produce a skill program which could generalize to a far greater number of examples.
We have no way to quantify generalization, to quantify abstraction, for instance. So I think there is a need for an ambitious new benchmark that will be focused on measuring precisely generalization capabilities, right? Generalization strength, and not just skill at a specific task given sufficient training data, which is not very interesting. So you could think of it as a sort of IQ test that would be applicable to machine learning algorithms, but also to humans, ideally, so that we could compare the capabilities of our creations with the capabilities of humans. You could call it a GQ test, a generalization quotient.
So what then is a real display of intelligence? In Chollet's framework, intelligence is something that your priors and your experiences do not prepare you for. In Chollet's framework, if you have a problem that's this hard, and your prior knowledge and all your experience to date only get you this far. The difference is what you have to use intelligence for. And therefore, if we measure intelligence, we should look at all of these quantities. We should look at how hard is the task, and to which part can your prior experience and also your data that you have collected so far help you in solving the task. Whatever's left, that's intelligence.
Chollet cites the example of a sorting algorithm. With a few lines of code, you can write a sorting algorithm which would generalize analytically to any permutation of numbers. For a deep learning model to do the same thing, it would need to have a dense sampling, arguably of every single permutation of numbers. Chollet points out that previous conceptions of intelligence were based on expert systems and knowledge. If only we could encode human behavior as logical predicates, and if only we could encode human knowledge using databases and knowledge graphs, then we would solve intelligence. Machine learning came along and it changed the game significantly. It started to become about learning. But not only learning, Chollet would argue that the most important concept is generalization. And when we solve generalization, when we can have an intelligence that can produce a skilled program which generalizes, then we've solved artificial general intelligence.
The first definition of generalization presented in the paper is the difference between system-centric generalization and developer-aware generalization. So I think it's useful to think about this in the context of known cross unknowns with respect to these novel encounters that we're going to expect our system to face.
One of the key contributions from Chollet in this paper is the ARC challenge and Kaggle competition. It's essentially an IQ test, but with a much higher diversity of tasks, and none of the tasks have been procedurally generated from a static master program, which makes them harder to reverse engineer, and you have to create skill programs that generalize from just 3 examples of these tasks. Deep learning methods are not applicable. One of the key reasons that Chollet introduced the ARC challenge was to demonstrate developer-aware generalization. As a developer, you need to create a solution to this, which will work on a task that you've never seen before. Chollet also argues, in stark contrast to Legg and Hutter, that there is no universal intelligence. He believes that we should have an anthropocentric view of intelligence, and the artificial general intelligence that we create should be able to perform the same sorts of tasks as humans, and we should imbue the same sort of core knowledge that humans have into these algorithms.
Chollet makes a difference between prior skill, experience, and intelligence. In this case, probably evolution has endowed me with the ability to plan my way through any uncomfortable terrain. So Chollet says that might not necessarily be intelligent because it's already built into you.
So to be clear, it is very good at pattern recognition. And I'm not in any way trying to downplay the significance of being good at pattern recognition. This is actually immensely useful. Deep learning is applicable to a tremendous scope of very difficult and important problems in machine perception because they are pattern recognition problems at heart. But importantly, deep learning is not the road to artificial general intelligence, right? Scaling up deep learning by adding more layers, adding architecture search, using these deeper models or training on more data is not going to get you to AGI.
So Chollet thinks that we should create a meta-learning algorithm that could create the kind of high-level rules and reasoning that humans would in respect of the same task. Francois Chollet retweeted me. Ding! I was over the moon. It was a real passion project for me, so I thoroughly recommend to go and check out the feature-length video on the measure of intelligence on Machine Learning Dojo. Make sure you also check out Connor and Yannic made their own videos about it. Yannic is actually planning a 4-part series, so the first part has gone out, and after we release this, I think Yannic is going to release the subsequent parts, so keep an eye out for that. Remember to like, comment and subscribe. We love reading your comments, and we're going to be back for a very special episode with the team from Facebook who wrote the transcoder paper. This is the neural network that can translate from one language to another language. It's incredibly exciting, and we've got the entire team from Facebook joining us next week, so I hope you join us for that. Peace out.
I hope you enjoyed this conversation. We're trying to make sense of all of this, which is a huge topic. Leave us your comments and suggestions and all of that.
Hello folks, and welcome back to the Machine Learning Street Talk YouTube channel with me, Tim Scarfe, my 2 compadres, Yannic Kilcher and Connor Shorten. We are going to talk about François Chollet on the measure of intelligence. This is a really interesting paper. François seems to think that current machine learning methods are brittle and data hungry. They don't generalize very well, either from the training data that they were trained with or from the assumptions of their creators. They can't really deal with novel tasks. And there's been a real focus on narrow-based skill as opposed to generalization. He thinks that we need to have an actionable measure of intelligence. He thinks that a lot of the skill-based methods now can be bought, but just by throwing lots of computation at the problem. I would say Francois is probably one of the most popular critics of deep learning. What do you guys think about the paper?
He's mainly concerned with intelligence, right? So it's not that much a criticism of deep learning, but it is a criticism of people who call deep learning systems intelligent, which is prevalent today because the entire field is somewhat nicknamed AI. We'd much rather define it as machine learning, but in the popular literature, this is known as AI. And I think that's where the criticism comes from, the fact that Chollet says maybe these things have not really much to do with intelligence.
Yeah, I think it's interesting the levels of generalization, talking about local and broad generalization, and how the lines get blurred between going from local generalization, which could be something as like, is it robust to adding a noise map, down to can you rotate the image or perturb a single word in the text classification task, up to broad generalization where it's things like if we're doing cats versus dogs and we add a new dog breed, how does it react to that? And there's a lot of the things I think are interesting, this idea of system-centric versus developer-aware generalization. His kind of criticism of superglue favoring the animal AI benchmark I thought was interesting as well. And the discussion of the chess playing program that beats Garry Kasparov and then it's no longer intelligent. And then he compares that to AlphaGo and AlphaZero. But I think mu0 is actually something that's very applicable to things like robotics, and even talking with Harry about model-based reinforcement learning, I think the mu0 algorithm is generally applicable. So excited to talk about that, but I think it's totally different, the if-else chess algorithm and then this model-based mu0 algorithm.
Yeah, well, I'd love to get into that. I think in the beginning of the paper, Francois talks about the history leading up to that. And he says that we started with expert systems, and there was this guy Minsky who had this conception of intelligence, which was based on it just being a collection of skills or being able to perform certain tasks very well. And they didn't really have the concept of generalization. And if they did have the concept of generalization back then, they felt that it was just solved by adding more knowledge to your knowledge graph. It was only really when machine learning approaches came along in the 1980s that the word learning and the conception of generalization as a first-class citizen was really discussed.
Chollet goes on this whole 360 here, where he starts off by saying that, measuring skill is not really the same as measuring intelligence. If a system is good at one particular task, it doesn't mean it's necessarily intelligent. And he says, people thought once we could solve chess, that required intelligence and so on. He goes through this whole thing to come back to the ARC challenge, which is basically, here's a bunch of tasks. If you solve them well, I'm going to think your system is intelligent, right? So it's important to point out that I think this doesn't really shine through in the paper, is the only thing we can measure is skill. That's the entire problem, right? The only thing we can really assess is how well you do at a particular task compared to some other system. And I think the whole paper, if you have to almost read it in the light of how do we come up with sort of the perfect task that we can measure skill, but that still gives us a good indication of intelligence or generalization capability. What he frames as intelligence is basically generalization capability, right?
This G factor idea is really interesting, trying to find like the common task that all these different tasks like Rubik's Cube solver, maze solver, write a poem can all do this one G factor hierarchy of cognition. I really like the physical fitness analogy where he says the marathon runner, the bench presser, and the basketball player, they all have this common like lung capacity thing at the top. So you can try to do that. So what do you think about that kind of like my take on that was that there's like this catastrophic forgetting phenomenon where it's like a model that gets really good at classifying ImageNet would forget to do this G-factor task.
Yeah, you mean like a model that can, the more you specialize on a particular task, if you do it in a machine learning way, the model would actually forget how to do the other tasks. Is that's
right?
That's this catastrophic forgetting, right?
Like, I think catastrophic forgetting is unlikely to follow this hierarchy. It might maintain the specialized skills and forget the general thing. So I think that would be the key challenge to finding this generalizable task, that input-output measure that it can all do this one task.
Yeah, exactly.
One of the kind of controversial things that Chollet says, and we'll get into this in more detail, that there was Legg and Hutter in about 2007, I think they wrote a paper which was formalizing a definition of general intelligence. And it was completely different from Chollet's conception. And Chollet explicitly says that he doesn't like what Legg and Hutter came up with. But Legg and Hutter's definition is what's being taught in universities now. If you look at the latest DeepMind set of lectures, they were teaching it in UCL just a few weeks ago, and they were teaching Legg and Hutter's definition. And we'll get to that. But Chollet thinks that intelligence should be anthropocentric, so it should be very human focused. And coming back to what you were saying, Connor, about the physical fitness level, I think that's super interesting. He says that physical fitness level is a bit like a latent variable. It's a constellation of interdependent factors. It's based on what your lung capacity is, how long your legs are, and various other characteristics that you have. And intelligence is a bit like that as well. And there are many factors that correlate with your general intelligence.
Well, I had someone, I don't remember if it was on Reddit or on a YouTube comment that took a lot of issue with this G-factor notion. But I mean, the surprising thing about human intelligence testing is that if you do the statistical analysis, the model that explains best how the humans perform on different tasks is a model with one shared factor, right? It could have come out very differently. For example, personality tests are best explained by 5 factors, or you can, I guess, subdivide those into 10 factors. But intelligence appears to be best described by a single factor. And that's something that's, I believe, that is very surprising. That's not just, I mean, this hierarchy that Chollet says, that you have this common intelligence thing, and then that's not obvious. It's not this, the world didn't have to come out like this, right? But it appears that humans have this general intelligence factor, and that motivates the entire thing. So I believe that also justifies to say that an intelligence measure should be human-centric, because human intelligence is the only intelligence we know.
It doesn't surprise me that there is a general quotient of intelligence, because all of the human cognitive tasks that we perform have an interdependency on sub-skills. For example, if you have a poor working memory, that would negatively affect your performance across a wide array of tasks. So it doesn't really come as a surprise to me.
Sure, but you could imagine, there being 2 different kinds of intelligence, right? So you could imagine saying, like, this person is very good at intelligence A, that means very good at, I don't know, these kinds of tasks, and that other human is very good at these kinds. Now, that's true in general if you just consider tasks, but if you consider cognitive tasks that we would include in IQ tests, then you don't find this split. You don't find these 2 independent directions, or 3 or 4. You find one single direction. And that, I mean, you can say, yeah, okay, but it's not entirely obvious from the start. There could be more.
I suppose one of Chollet's justifications here for placing a scope on different tasks is that if you look at all of the possible tasks that could exist in the universe, it's not really very meaningful.
Yeah, of course. I mean, it's to me, it's fairly obvious that you should make an intelligence, especially if you go for, building an AI that sort of is compared to humans, that you should go for a human measure of intelligence.
Indeed. So Chollet thinks that Garry Kasparov was intelligent because he quickly learned generalizable skill programs. So it's not that he's good at playing chess now, it's that he had the capability to learn it quickly. Chollet argues that modern machine learning is skill orientated in this setting. I characterize Chollet as saying he thinks that deep learning techniques are glorified hash tables. And I personally think that is a fair characterization based on what Chollet said, but it's a little bit hyperbolic, so I'm sorry about that. But he thinks that skill can be bought with unlimited priors and training data. He introduces different types of generalization, so he formalizes levels of generalization. I think he has a bit of a go at some of recent moonshots in AI. So, for example, AlphaGo, he thinks that we're barking up the wrong tree, essentially, and that we're still focused on skill-based learning as opposed to learning something that can generalize. Of course, the folks at DeepMind would argue that their system can generalize and it learns the rules of the game as part of the training process, right? But if you even change the board size by 1, you would have to retrain the entire algorithm from scratch. So you could argue that that isn't really indicative of generalization at all. But Chollet also argues that all intelligence is relative to the scope of the application. He thinks that AI should be benchmarked against human intelligence, so that there should be an anthropocentric scope of tasks when we measure intelligence. And by extension, he thinks there is no such thing as universal intelligence, or that we shouldn't be thinking about universal intelligence. He also thinks that human-like general intelligence should be founded on explicitly described knowledge priors. So there are certain things that humans understand, like we know what dogs are, and we know what cats are, and what arrows mean, and what ladders mean, and so on. So he thinks that if we were to create any artificial general intelligence algorithms, that core knowledge should be imputed into the algorithm.
Yes, there are lots of things here. So first of all, I have some kind of different opinions than Chollet on these kinds of things. And so in some of these things, he tries to make it very formal, but I feel that he sort of, it's kind of made up, like these different levels of generalization. Okay, so you can say, okay, skill-based generalization is something we can measure, but after that, it sort of gets washy, right? And it's sort of you're taking the point of view of a human right now that looks at deep learning and says, what can deep learning do? Okay, we're going to call this skill-based generalization or narrow generalization. And what can't deep learning do yet? And we're going to call that broad generalization, right? I feel it's a very 2019, 2020 view of the world. I feel it's less formal than he writes it. It's more washy-washy. The same with his notion of system-centric generalization and developer-aware generalization. It makes sense to say that you should consider generalization in light of all the information that went into a system, which includes the human programmer, right? So you should take the human programmer of a system into account. But by extension, you should also take into account the programmer of the human programmer, which are the human's parents, or the culture around the human, or the evolutionary process that made the human. And if you go back, then everything is as generalizable as everything else because everything came from the Big Bang. And if we really, really capture developer-aware generalization in a broad manner, we would include the process of the Big Bang. And so these things I sort of have an issue with that they appear to be less formal than they're stated. And then the last thing I just thought of is this AlphaGo, saying that, okay, because AlphaGo doesn't generalize to other tasks and sort of you can buy the skill at Go by throwing lots of resources at it, and that's not intelligent. I sort of take a different measure in that a human by itself could not learn in this amount of time how to play Go this well, right?
But
and maybe a machine by itself without a programmer cannot either. But the human-machine combination, if I buy DeepMind right now, right? If I buy DeepMind with all the people, that thing is incredibly intelligent as a human-computer interaction module, right? It can learn faster. It can generalize to new tasks so extremely fast, not only because it has the humans or the machines, but precisely because of the combination of both. Right? So the system can generalize extremely well. I wouldn't see AlphaGo as a failure necessarily, because we thought Go was about 10 years out, and they demonstrated, no, you can learn it much faster. And that very much fits Chollet's definition of intelligence. That's a rapid generalization to a new task.
Yeah, when Lex Friedman interviewed David Silver, he said something really interesting. He said that the canon of Go knowledge wasn't created by one human being. It was created by many, many people playing Go over thousands of years. And AlphaGo discovered some new strategies that weren't previously known. And now humans have started to incorporate those strategies. So I love this notion, and Chollet points this out, that many things that we don't think of as being intelligent, especially collective entities, things like markets or companies or even science as a process, that they are intelligent, but we don't necessarily recognize them as being so. But this is another thing that Chollet argues for, though, is that the information efficiency of acquiring skills is important. It seems quite wasteful to brute force search all of the possible situations in the future in order to derive a strategy and to learn something.
Well, maybe. I see what he means, but AlphaGo figured out a way around this, right? The tree search is too expensive in Go. Even in chess, even in Deep Blue, the tree search was too expensive. So you had to heuristic it up and do whatever your min-max search and whatnot. And that's not the same thing as brute forcing it. And that is a rapid generalization to this new task of the human-computer system.
Well, that's another one of our favorite topics, right? Is like the policy network is the system one thing, and the Monte Carlo tree search is our system two reasoning. But so really quick, I want to stay on this idea of local and broad generalization and system aware and developable. So this paper, DERMGAN, it's harvesting the generalization power of generative models to diversify the data set and then enhance the classifier. So sorry to our viewers if these pictures are a bit too much for them, but so with these skin classification pictures, so you take these semantic masks and you can move around the location of the mole that you're in question, the lighting conditions, the skin color. So we can use these generative models to expand our scope of our known unknown. So we know that there's going to be the lighting and the location of the mole, and so we can use these generative models to augment those data sets. And then we also have these world models. So this GAN thing is pretty interesting to me. They put this whole Pac-Man model, they don't really completely get it in there, but it's getting close, and I imagine it'll get better over time. But if you could imagine putting the entire DeepMind control suite into one of these generative models, or even the ProcGen benchmark, it has this interesting, now we're talking about generalizing in these generative models. Let's say you take all 57 Atari games. That might not be enough, but how long until you can produce a new game? Learning these underlying rules with the generative models. And so if we have generative models, then we can kind of produce new data that dramatically improves our ability to get known unknowns. Harvesting the power of generative models is the next step. That's what I think is going to happen to go from local to broad.
It is a good point, right? Because so in terms of this Chollet framework, he talks about these known unknowns. Let's say that's data augmentation, right? If those are my known unknowns, I know that my image can be flipped, and in my test set, a flipped image should have the same label and so on. Now, with what you're saying is pretty interesting, because if I build a generative model of the data, I don't know what it's going to produce per se, right? And I'm going to build in some priors because of my architecture, but that would already cross over in my mind into these unknown unknowns, because now I am letting that generative model of the data produce training data, and I don't exactly know what's going to come out of that, right? And then I'm going to train my classifier on these data points that I didn't know existed before. So I think that's a pretty good point. Of course, the counter question is something like, there's no new introduction of data in this process, right? Because you build a generative model over the same data that you train your classifier on, and then all the additional information theoretically is simply coming from the architecture of the generator. So maybe that just expresses a failure of us to properly build a classifier on top of data.
You recently made a video on the synthetic Petri dish paper, and I've been really into the generative teaching networks thing where we use this objective to produce the data in the generator. Like in generative teaching networks, the goal is just learn a classifier on CFAR 10 like as quickly as possible, and then it produces this data that you might describe to a human as an unknown unknown. A human would never design that data set. It's like complete noise. So maybe like it can just optimize the object, like can use the generative model in a way to search for these unknown unknowns. That like definition, we can't possibly be in the loop, right? Like
yes, that's a good point. Yeah.
There's generalization to data and tasks, right? So in this case, the known unknowns, is that just another way of saying interpolating, or is it another way of saying any data which is on this manifold? So there's generalization to something which is off the manifold, and there's also another type of generalization which is doing a slightly different task. It might be instructive just to look at this spectrum of generalization that Francois talks about in his paper. So in his formalism, Yannic talks about system-centric and developer-aware generalization. So system-centric is generalizing, let's say, to images we've not seen before. And he says that the generalization power due to prior knowledge is currently ignored on this metric. So an example of this would be, I'm building an ImageNet classifier, and it only generalizes to things which the developer had conceived of. So for example, the test set on ImageNet. Whereas this developer-aware generalization is about handling situations new to the system and the developer. But is it talking about data or tasks?
You can conceive any task as data.
I think a good example with the DERMGAN paper I showed earlier would be like a system-centric or like a developer-aware thing would be knowing that the skin color is going to change or the location, and then maybe an unknown unknown would be just like new kind of melanoma or a new way of it, like a totally different way.
Yeah, it goes up all the way, and that's what I've been like. That was my point at the beginning, where he's simply characterizing as the known unknowns, this tight generalization, as whatever we can do right now. And so he says something like, oh yes, of course we're going to expect, the thing to change a bit, its location and so on. But so that's tight, that's narrow generalization. Broad generalization would be something like, can this AI also solve other types of skin disease problems, right? Not only because we train it on melanoma, now can it also solve other, and then, but as soon as we come up with a deep learning data augmentation method that does this, he's going to redefine and say, oh, but that's narrow generalization. Can it also do other medical types of tasks, right? And then, it seems like the borders there are very much focused on what we can do right now. Because 10 years ago, he would have said something like, sure, you can train a classifier to classify melanoma, but can you also train one that then generalizes to where the melanoma is in a different place in the image? No, you can't. Right?
I think one thing that confuses me is just the predictive architecture is very fixed and closed domain. We spoke about POET, which is this kind of open-ended learning. And it brings me to the Wozniak Coffee Cup challenge. I know Yannic's got some interesting comments to make about that, like having an IQ test before you're allowed to go into the room. But Chollet cites this as being an example of broad generalization. So what if you could have an agent go into any room and make a cup of coffee? That must be broad generalization. And this agent, because I suppose what the reason I'm thinking about this is before we were talking about an ImageNet classifier generalizing to data off the manifold or data from a different test set or something. But that architecture is completely fixed. Whereas if you're talking about an agent-based reinforcement learning algorithm that could control a robot, that's a fixed architecture which could, in theory, be able to generalize to making a cup of coffee in a lot of different rooms.
Yes, but imagine we just become, first of all, we become extremely good at sim to real. right? So that we don't need many real-world training data. And then second of all, for some reason, someone just writes a really good simulator of all the possible rooms with coffee machines. Like, there's this, I don't know if this is a myth, but I hear there's this building manager game where the elevators are so good. There's this like super old computer game, so that elevator engineers use that game to test their elevator algorithms or use like mods of that game. So imagine someone just comes up with an extremely good simulator of that, where literally all possible thinkable situations happen at some point, and you could just train forever with your 50 billion TPUs or whatever we have at that point, like MPUs, whatnot. You train, and then you do the sim to real, you adapt very quickly. What Chollet would say, like, no, that's not intelligent. You bought this with a lot of data, right? So coming in with this robot example and saying like that's an example of broad generalization, I can take Chollet's own viewpoint and say, no, you have to condition on how much experience it's gotten. It's only broad generalization when it has gotten little experience in coffee cup filling and can do this type of stuff.
I think in order to learn your simulator, you're never going to be able to enumerate all of the rooms with the coffee cup. So it becomes like, how can we learn our model or our simulator with as few examples as possible? So I just think skill acquisition efficiency, we should be talking about the generative model, because like if we have this perfect generative model that's learned the natural image manifold, and then we have a data augmentation search technique, we can just enumerate what we need, get the unlimited experience. And then it becomes like tic-tac-toe, where there's no generalization needed because we've seen every possible room that makes sense. But then it's, practically though, how do we learn these generative models? Because we have 57 games, right? Now we want to introduce a new game. That's the question, I think.
Chollet would also take issue with your generative model, because if you had a perfect generative model, the question is, how did you learn it? And if you learned it with very few samples, in just from today's standpoint, that must mean your priors that you built in are so excellent, right? Are so attuned to the problem you're trying to solve. He would then also argue that something is not intelligent if you've put a lot of prior knowledge into it. So his two things are, something is not intelligent, even though it performs well, if it has had lots of experience, or it has had...
It'd be interesting to contrast the WOZNIAK coffee cup robot versus AlphaGo. AlphaGo, the environment is a board. It's a discrete space. And the algorithm, Chollet would argue, has no generality whatsoever. I might argue that it does, in the sense that the networks that model the board use a convolutional neural network, and that has this translational equivariance. So it will know that this pattern of stuff over here is similar to this pattern of stuff over here. So there is some generality, but it is actually really rigid, though, isn't it? Would it be even harder to do something like that if it was a robot making cups of coffee? Because that space, if you imagine all of the possible worlds that this robot could live in, that's vast compared to this fixed board that you play Go on.
Well, to continue on this, like, I can play 7x7 Go pretty well, but 19x19 Go, I'm terrible at it. So it's a bit of a more dramatic transition compared to like a red or a blue coffee mug, or maybe it would be like encountering a whole new coffee machine. But the transition, I think, is very dramatic.
Well, I can say something that's sort of countering that, in that, because you're now starting always from the beginning, where it's always the same Go board. But if I simply cut off the start of the game, it's an entirely different situation each time. Of course, it's always on the Go board, but it's entirely different, right? And every single situation is inherently complex. Like, one stone that's a bit to the left or to the right or missing makes the game board entirely different. And it's just a matter of numbers, I feel, because in this coffee cup example, here's the periodic table of elements, right? And ultimately, every single kitchen starts with that and is simply built upon the periodic table of elements. And in fact, it's probably some combination from IKEA. And so I feel it's just a matter of scale, but the principle isn't that much different, I think.
You could certainly argue that the older AI systems like Deep Blue, they required explicit programming from humans down to a great level of detail. You could argue that some of these new deep learning systems, they are implicitly programmed because they are trained to a certain extent on lots of data. But you could argue, though, that AlphaGo is very much like Deep Blue in the sense that it has this policy network, but it's still doing this Monte Carlo tree search, and it's kind of recursively looking ahead. It's planning, and it's looking at all of these potential future situations. So that, even though that would in sense generalize to many other types of game, it still seems to me like there's a lot of human knowledge encapsulated in that algorithm.
Sure, but any coffee cup robot is going to have like a giant amount of human knowledge encapsulated in it. I just don't see why the coffee cup example is so different from the AlphaGo example. Ultimately, each Go situation is ultimately different, except it's on the same board. And I can make the same argument and say each kitchen is ultimately different, but it's made from the same stuff. It starts from the same point. The makers of the house decide to arrange it in a different way.
What about like the adversarial nature of it? Like the fact that you're not just like making the coffee thing, things are pretty deterministic. If you pick up the coffee, it's, likely to just move upwards. It's not going to like differently all of a sudden. So I think that adversarial component of it actually does totally change the two tasks.
I'm not sure. You simply have an environment, and in Go, the environment just always responds. You can just assume it always responds with the optimal action.
Well, the criticism of Go is the chess is like once it goes out there, then they open source the model, and then people find these adversarial ways of like these little things that like, if I found this way to exploit the model's lack of knowledge. And so that's why we're like, oh, it's not that good compared to the coffee robot, where we don't really like test it with these very bizarre little things.
But we could do just the same. Like if I build this coffee robot right now and it can go into any kitchen and so on, I'm pretty sure if it's built on current technology, it's going to have like some CNN in it. And then I can build an adversarial example for that CNN, put it on the fridge, bang, and the robot will just be completely, disturbed by it, like AlphaGo is. But the analogy would be if I told you without building AlphaGo, what if I had a robot that could play Go and beat any human? That's like saying, what if I had a robot that could go into any kitchen? I don't see the distinction there, except the scale, except the numbers. Even if you go by Chollet's definition of intelligence, it's simply a matter of how much prior goes into it and how much experience goes into it.
So what do we think about these priors, like this idea of unlimited priors? And we have the CNN prior, which is really great, this local kind of dependency in images. But so how do we find these priors? There's the idea of the core knowledge, right, where he names like 4 priors that humans have. But that, to me, though, is like the idea of the input-output way of testing for the priors, right? Like, how else do they find these core knowledge priors?
I guess someone sits down and thinks, okay, what do all humans have? And then I guess you can do some kind of tests, but it seems like this is entirely speculative, right? These priors that humans have innately, who knows? Even harder, because basically says you should build a system that has the same priors built in as humans. And that is so hard. I have made the argument when I looked at this art challenge. He says something like, yeah, you should build in the priors of human core knowledge into a system that if you want to compare it with humans. And to me, that task is as hard as solving AGI. Like, if I could perfectly programmatically describe all the priors that go into humans, you could build AGI.
Well, so that would be my question, though, is how do we then, like, finding the priors seems to be like this manual process of like try and fail and repeat. And like that's how we come across the CNN, these ideas like curriculum learning or data augmentation, like consistency regularization. Mine would be interesting to try to like, so to me, the best way of doing this would be like a large scale evolution search and not use gradients to try to find priors.
The question is always, what do you search over, right? For example, one prior that Chollets says humans have innately is the objectness prior. The assumption that the world is made of objects, that these objects are somehow local, have boundaries, and can interact with each other by sort of contacting each other. How do you even construct a search that would result in something like this? So to me, that's far away. And I think his argument is more that if you want to build an AI system, you should explicitly program in the notion that there are objects. But how to do this? Who knows? And if you go by his reasoning, you should program in this objectness prior exactly or as close as possible to how humans have it innately, right? It's not like it's written down. It's an object is like much more. We can't even define it really in language. In order to compare it, you should program it as closely as possible. And my argument is that if I could do this for all of the human priors, I would already have AGI.
So I think it goes a little bit back to, well, first we can't have catastrophic forgetting. We can't have these neural networks that learn tasks and then forget object permanence. So I think that would be the first thing to solve. And then we could have this like multi-objective optimization with something like generative teaching networks or synthetic petri dish if we scaled up the computation, where the objective is like perform all these tasks. So it's kind of now transitioning into his criticism of super glue and the animal AI Olympics. What do you think of these benchmarks that are like a combination of tasks?
Yeah, I mean, he probably makes the point that you still know the tasks beforehand, or you still know what kind of tasks appear. And that's what I find so interesting about this ARC challenge. Like, I really disagree that solving the ARC challenge will give us anything intelligent. Like, I'm going to make this call already before we have it. Usually people make that call after you have a system like this. I'm already going to make that call. But I find it a super interesting challenge by itself. But he would argue that you still know the tasks that are coming at you. And you should build a system where you don't know the sort of tasks that are coming at you. Now, of course, in the ARC challenge, you know the task in the sense of, you know, the input-output format. But the logic behind the task you have to rapidly acquire. And I think that's like a subtle point he makes. But I think when he says you should pre-program human priors, he wants to say, because he defines these different kinds of priors, right? So he has like, oh, you have the reflexes that you get hit, you like flinch. We don't care about this. And then he says you have these objectness, navigation, and so on. Those you should pre-program. But then the last set of priors are the meta-learning priors, like your learning strategy. And that he considers that's intelligence. So, but I don't see I don't see a distinction between that and these other priors. Like, if I could exactly formulate the meta-learning strategies that humans have innately, again, I would solve AGI.
I looked at Shane Legg and Hutter. That Shane Legg actually had a great presentation on YouTube, and one of the examples is this kind of intelligence test question. So you're given a sequence of numbers, 1, 3, 5, 7, question mark, and you need to find what the rule is. And maybe the rule is 2n-1 because it's just all of the odd numbers. But it could also be 2 minus n plus, and then this series. So n-1 times n-2 times n-3. Now, as humans, we have this kind of built-in Occam's razor. So we would favor the simple solution. We would assume that the answer to this intelligence test is the simple answer, right?
Yeah.
Legg and Hutter, they formalized their definition of universal intelligence. And this looks very, very similar to anyone who studied reinforcement learning, I guess would have seen something similar to this. So it has the concept of an environment, an agent, a success function, and then you're summing the complexity, the K is the Kolmogorov complexity, over all of the possible environments. And that is the canonical kind of measure of intelligence which is being taught. So there's a screenshot here of Thor Grappel teaching this at UC recently. They just put it on YouTube.
If I understand this correctly, this measures over a range of environments. Whenever the agent succeeds in that environment, it gets a bonus that is inversely proportional to how complex the environment is.
That's right. Yeah, this complexity thing is Occam's razor. So it's favoring the simpler solutions.
But it's the environment that's in the Kolmogorov complexity. That's what confuses me, right? The K it's K of mu, and mu is, the arrow says environment.
So favoring the simpler environments.
No, I mean, but, right, it doesn't say the complexity of the agent that solves the environment. It simply says the complexity of the environment. So you'd get a higher reward for solving a simpler environment. I mean, that to me makes just little sense. If this were the complexity of the agent, like if you find a particularly simple agent that solves this environment, then that's more intelligent. Then I could sort of make sense of it. I'd still disagree, but I could make sense of it. But here, it seems like the agent's complexity is nowhere to be found.
So the measure of success, this is for one agent, and it's a function of the success valued over all of the environments, but the value is weighted by the complexity of each individual environment.
Okay.
Well, that's bizarre too, because binary string that encodes the environment is, are we compressing the whole environment such that we can measure the complexity of it, right?
You just assume that you have a function that gives you the shortest possible program that generates this environment. So okay, so this is for a single agent. You sort of have the expected success rate over all the environments, but weighted by how complex the environments are. Now,
yeah, so in the case of AlphaGo, would there just be one environment?
Well, who knows if you consider... No, I think you can formulate each possible board situation as a different environment. So the initial position would be the simplest environment, right?
I think in connection with Occam's razor, it's like the simplest environment is most likely the most common environment. Maybe like if I'm a baseball hitter, it's best for me to be able to hit a fastball than to hit like a curveball or a slow pitch, right? So
yeah.
So I guess it's like the Occam's razor is this energy efficiency. Well, it's not, but translating it, comparing animal and machine intelligence is like we have this constraint where we need to be energy efficient. So we wouldn't bother with the more complex task that has the higher Kolmogorov complexity unless our success is really high at it or something. So it's like I'm only going to get really good at chess, which has high complexity, if my value is really high. So imagine this value on the scale of 0 to 1 is distributed, so it's mostly around like 0 to 0.1, and then right. And then I think
exactly. This implicitly sort of assumes the distribution of environments around us, right? And it goes over. I don't know what the scope of environment here is, but I think that's what Chollet's definition would be disagreeing with here, that the scope of environment needs to be the human environments, because even if an environment is like very simple or very complex, it doesn't matter if it's not relevant to us. And I tend to agree with Chollet on this particular part. Like with all of these measures, you can always sort of pick them apart by considering, okay, over what is this over, and so on.
I mean, it might be worth just quickly looking at Chollet's formalism of intelligence. First of all, he introduces the generalization difficulty.
This definition of intelligence here is very much attuned to having a training set and a testing set, right? That's it. The definition that is formalized in Chollet's paper has always as a basis that you have a training set, and then you need to generalize to a testing set, and your intelligence is proportional to how well can you solve the test set from the training set, conditioned on your priors and experiences. And I think this Legenhutter definition has something completely different in mind when they talk about intelligence. So Chollet is much more geared towards a machine learning context, I feel, because he explicitly says, okay, you have like a training set, and you need to generalize from the training set instead of just considering, oh, how well can I solve problems? What you want to do is you want to look at a scope of tasks. And he makes the first part of the paper is basically arguing why we should consider intelligence always as a scoped over a particular set of tasks. And he's arguing that those are the human tasks, but intelligence for a scope of tasks, and now you simply average across all of these tasks in that scope. So you say, how well can an agent solve all of the tasks in that scope? And each task is now in this special form where you have a training set and a test set. Now, other than in machine learning, these can be way harder. So the training set can be, like we're going to see in the ARC challenge, something like, I give you 3 examples of a logical puzzle, and now I'll give you a 4th one, and you need to tell me what the solution is. So you simply average over all the possible tasks in this scope, and your score in each task is going to be how well can you solve the test set, which is basically your generalization difficulty if you're given the training set, but you always divide by this prior plus experience. So you say you're more intelligent the better you can solve the test set from the training set, but you're less intelligent if the human programmer has already built in a solution to this, because that would not make you intelligent, that would make your programmer intelligent, or if the human has provided you with lots and lots and lots and lots of examples of this task already.
How would you formalize all of the tasks in a scope? What would an example of a scope be?
Well, that's the entire question, right? That's the difference between what I feel Chollet and these other definitions, because the scope can be every conceivable task in the universe, every possible task that humans can come up with, every possible task that I, François Chollet, can come up with in these 2 months that I work on the ARC challenge. That's, again, it feels like if I could exactly formalize all the possible tasks that the human task scope, if I could formalize all of them, would that already solve AGI in this form? Like, there's a pretty good argument to be made that if I could formalize the tasks, I would have already solved AGI, or formalizing the human scope is as hard as solving AGI.
But this seems so much better to me. Just coming back to this formula. So Chollet is saying the intelligence of a system is a function of the scope of tasks, the function of a curriculum to learn those tasks, and then for every single item in the curriculum, multiply it by the generalization difficulty divided by priors and experience. That to me seems very logical, because when we come back to Legenhutter's definition, it's only talking about maximizing the success of an agent in as many environments as possible.
I think the first problem with that is this idea of like measuring the generalization difficulty easily, right? Like that would be so hard to try to predict the generalization difficulty of a task. I think that's one of the NeurIPS 2020 competitions, is trying to predict generalization of a model. And
that's what we were saying up here. The function of the complexity. So this efficiency of being able to acquire new tasks is something that Chollet's interested in. So
you have the optimal training solution there, right? So it basically means if I had a master oracle that gives me the optimal training set solution. And this, you imagine like a neural network that completely overfits on the training set. Like the shortest possible program that can solve the training set and only the training set to optimal precision. If I give you that, how much more do you need to know to solve the entire task? And by the entire task, I mean every possible test set. So the entire task could be something like differentiate cats from dogs, whatever image I give you. And then I say, here is a training data set with these 5 cats and these 5 dogs, right? And the generalization difficulty is going to be, if I give you the perfect solution on the training set that doesn't care about generalization, how much more do you need to know about, how much more work do you need to put in to solve the entire task? So if it just happens to be such that the top left pixel is always blue for the cats and always red for the dogs, then the optimal train set solution helps you nothing. There's no information about the global solution of the task. But if I give you a decently sizable data set, right, and it turns out that it's easier to actually describe what a dog is and what a cat is in terms of visual features than it is to just hard code the training data, right? It's shorter, the program is shorter, the weights of the neural network are shorter than remembering the training data. Then that solution would actually tell you already a little bit about the entire task. So the generalization difficulty would be easier for that task. So you have a notion of training data set already there. The more you can read from your training data set about the test solution, the easier the generalization is.
This image is quite instructive as well. This is something that Chollets talks about a lot. He says that in a lower intelligence system, there is a lower information conversion ratio. So your operational area is generalizing in a much more shallow sense compared to a higher intelligence system, which, as you can see, has a much broader generalization in the space of situations from what it saw during training time.
Well, so what about like sparse factor graph being like most data efficient way of learning these causal relationships between the variables? And then on the other hand is like a generative model that's learned like the image manifold and now can like, this one can quickly do the distribution alignment with the new task. This one, the sparse factor graph is more data efficient, but the other one is like more powerful, I think. And it's like machine intelligence. I think that's the difference is like the human intelligence needs to do the sparse factor graph thing, whereas the machine can do like this dense sampling generative model.
This sparse factor graph idea that we discussed when we discussed Benjo's talk at iClear, that's sort of the idea that human knowledge or so is arranged in this sparse factor graph. That's a massive prior on the world, right? That's not just a simple prior. That's not like L2 regularization. That's like a very, very strong assumption on the world. And if it turns out that we are able to solve tasks because we have this strong prior, then Chollets would say, you have that strong prior built in, right? If you can solve a task because of that, you're not really intelligent because you have that prior. And on the other hand, he would also say, a deep learning system that you've just given loads and loads of data is not intelligent because it had this experience. He makes this axis of you can buy skill with lots of prior or you can buy skill with lots of experience, and neither is intelligent. And here, I guess here's where I disagree. I think the generalization capability of, if you say AlphaGo isn't smart because it had lots of experience to train on, the humans built AlphaGo to generate its own experience. Right? So, but the humans couldn't do that by themselves. So it's not like the humans, because in Chollets' definition, it is developer-aware generalization includes the programmers and basically says, you know, whenever you have gotten something from your programmers, it doesn't count in that case for the machine. But in my mind, it's like the symbiosis of the two. Neither could do it by themselves, but together they can do rapid generalization.
Well, I think AutoML 0 is the most open-ended AI algorithm out there, where it's just searching for the ways to construct the program. So maybe that kind of system where it's just searching for like how to combine variables, that I think could be something that's close to not being the human machine together.
Yeah. Yes.
But then that is so infeasible, right? Like AutoML 0 isn't gonna beat AlphaGo anytime soon.
But Chollets would argue that, he has this concept of an intelligence producing skill programs. So he would say that the intelligence system was humans and the skill program was the algorithm that we created.
Yeah.
Well, I suppose you could break it down, because humans created a skill program, but it was kind of like a meta program, isn't it? Because it's a skill program which can tune itself based on interacting with a simulator.
Are humans today more intelligent than humans 100 years ago?
In many ways we are. It's exactly as we were saying before. The canon of Go knowledge has been built up successively over generations, and the canon of human knowledge is also built up because much of our knowledge is externalized. It exists in institutions, it exists on the internet. We've never had a better collective memory system now than before.
Well, memory isn't the same as intelligence, right?
Well, it's a factor in intelligence, because if you were born tomorrow as opposed to in the 18th century, you would have the benefit of this pluggable solid state hard drive, which is the internet. And that's like an externalized mind in a sense.
Sure, but in terms of psychometrics, humans haven't really gotten more intelligent in the last 100 years. I mean, there's a little bit of this effect where every generation is a few IQ points higher, but it's not substantial. Like humans 100 years ago were pretty much as smart as we are today in terms of psychometrics. And Chollet is modeling his tests and his formulations according to this notion, the same notion that the psychometricists have, right? But I would argue that if you look at what Chollet says, namely how rapidly can you generalize to new tasks, humans today are vastly more intelligent than humans 100 years ago, because if you give us a new task, we can just generalize so much more quicker because we have computers, because we have all the kinds of things.
Well, here's another thing. If Connor of 2020 compared to Connor in 1520, I have these contact lenses that let me see the IQ test, and I can quickly understand the task. So that's like another thing with these psychometric tests, is like the computer vision system, it needs to like see the Rubik's Cube and process the state of the Rubik's Cube. And there's that lag between seeing and then representation that I think that we're leaving out of this. Like solving a Rubik's Cube and then solving a Sudoku puzzle, right? It's the vision, the perceptual. That's what we're doing with deep learning, right? Is solving perception. Like that's.
Yes.
So I think that's a huge part of this psychometric test. Is I can see the IQ test faster now. I'm not better at solving it, but I can process it a little faster.
I'm not sure if that would make a significant difference, but I'd like to pick up on what Yannic said, which is you asserted that humans now would have better generalization capability than 100 years ago. The whole point of these IQ tests is to test fluid intelligence, not crystallized intelligence. This is the direction that Chollet wanted to go in even further by increasing the diversity of tasks. You're reducing any kind of carryover, because now if you go on an IQ test, you already understand roughly how to solve it. So why do you think that humans can generalize better now?
Well, I'm riffing on these different definitions of intelligence. Like, why do we even model intelligence according to these psychometric tests? I mean, yes, we're somehow assessing a single human's brain generalization to these things, but I would argue that humanity as a whole can generalize so much quicker now than 100 years ago. Like an organism like DeepMind, you can throw a problem at that and it's going to be solved, but this is not captured by any of the intelligence tests. This isn't, so to say from Chollet, to say like, yeah, something like AlphaGo isn't really intelligent, technically true in this psychometric or generalization capability test that he develops, but I would say DeepMind as an organism, and I don't mean the people of DeepMind, and I don't mean the computers, but the symbiosis, DeepMind as an organism, is so much more intelligent than anything humanity had 100 years ago. That's what I'm saying.
Yeah. How would you measure that?
Well, in the same way, I feel there are these different issues, right? He says, okay, AlphaGo isn't really intelligent, but then we should look at generalization capability, which this is a clear indication of generalization capability. I throw Go at DeepMind, they solve it in a year or 2 years, right?
Yeah. The skill program that they generated does not generalize. Their intelligence generalizes.
No. If I measure each of the DeepMind people, I will find they're not much smarter than the generally upper, like high IQ people in the 1800s. It's the organism, it's the symbiosis that's smarter, that can generalize orders of magnitude more quickly than any of conglomerations of human and machines could generalize in the 1800s. So that's one notion of Chollet's. But then he also says we should model it after psychometrics. But by psychometric standards, we haven't gotten any smarter, right? And so I'm just saying that all of these things are so arguable and debatable, and you can, if you talk about generalization difficulty as intelligence, you can always construct these counter things that just make, like at the end of the day, you'll say like, oh, I still don't know any more than I started with.
There's also the information efficiency thing as well, because what you're saying is almost a step away from that, because when you look at DeepMind as an organism, there's a lot of inefficiency there. There's a lot of trial and error. It's a process which looks quite similar to evolution, actually. Lots of random things going on and the best things survive. That doesn't really help us when we're talking about creating an intelligent system on one computer.
I think it's like interesting that you might have this system that's like this one fully connected network, and then you have like these autonomous agents that it's like kind of this like the separate program theory of mind. Like previously we had this idea that it's like these separate things do these different tasks and then come together. Maybe we have like the separate things, but they're still learning based systems. Like we have our image classifier, and then we have like a learned data augmentation procedure, a learned consistency regularization, and like this kind of system of like structure and then autonomous learning agents within it. Might be my new favorite theory of mind.
Well, who knows? As you say, it's a constellation of many different things, and then you might get this emergent phenomena. This ARC challenge, it's fascinating to me because I think Chollet, what he wanted to demonstrate was that artificial intelligence doesn't really exist. This looks just like an intelligence test.
The big one goes to the small one, and that big one goes to that small one, and that big one goes to that small one. And what does the next big one go to? Right? You always have the number of demonstration examples, and then you have one test example where you do not know the output grid.
Absolutely. So the answer to this would be a grid the size of the black masked region here.
Yeah.
And it would be, of course, you could just use symmetry. So it would be something that looked like this area there, I would imagine.
Yeah, I mean, it's maybe for people who haven't seen this yet. So the ARC challenge consists of tasks just like this, where there's always an input grid and an output grid. And in each task, so this entire thing that you see here can be thought of as one training example. Right? And the label of the training example is where the question mark goes. And in each of these training examples, you always have multiple instances of demonstrations where somebody would like show you, look, this is how you would do that particular task. And then you have one test instance where you don't know the output grid. But I mean, this is super difficult. So the algorithm has to, first of all, decide how big the output grid should be. And the only training data, if you will, you get from this task are these examples right here. It's not like there is a big data. It's not like, in ImageNet paper, you see like, here is a bunch of examples of our data set. Like, this is the task. This is all of it. You get these 3 examples and that's it. And you have to decide how to look at that. The output grid isn't even the same size in all of these. So this is immensely complex. And you somehow have to figure out the rule from just these few examples. Yeah, so I love this task. I don't think it has much to do with intelligence, but I love this task. Absolutely.
Well, if I try to sell you on this idea of like the contact lens thing a little longer, it's like, don't you think there's a huge entanglement with your ability to perceive this and then get the logic out of it? Like, if you go back to that first one you showed me, the like pink, yellow, green tile thing, like it's more of like a perception task. It's like comparing where, like the task of where's Waldo to playing a Sudoku. Like some of these things, it's like perceiving it is crazy hard.
Absolutely.
Maybe that's a kind of prior that we have. When we look at this, we can just recognize the symmetry immediately.
Yes.
Maybe that's a very human thing. What would that look like for an algorithm? Would an algorithm be trying to... Because I suppose if you take a cell here, you could swap the coordinates and you could see if the color was the same. But what would an algorithm do? Would it just try all of these different priors, looking for symmetries?
There's lots of stuff in here, like the symmetry. For example, you only recognize the symmetry because it's in color, right? If this was in actual because the machine is not going to see this as colors. The machine is going to see each color as a different number. And if I were just to show you a grid of numbers, I bet you'd have a hard time recognizing the symmetry in this. Like, maybe we can try, but this is going to be like hard as hell for you as a human. So and this is one of the criticisms here, even though, this challenge is supposed to be, we explicitly list all of the priors that are in there. The prior that humans perceive color so abstractly, that's one of the things that isn't listed.
I know. There was that famous example in reinforcement learning as well, that we don't realize all of the human priors we have when we play a computer game versus an RL agent. We understand what ladders mean, that you can go up and down on a ladder. An RL agent isn't going to know that. But coming back to this, let's turn the thing on its head a little bit, right? Because one of the things that Chollets wanted to do with this ARC challenge was increase the diversity of tasks and also not procedurally generate the tasks, because if you generated them with an algorithm, it'd be easier to reverse engineer them. But what if it was framed as a machine learning problem and we had, let's say, hundreds of thousands of examples? What if it was just this symmetry task here and we had hundreds and thousands of examples? Machine learning would be able to find a shortcut and easily figure it out, wouldn't it?
Well, arguably, it would be able to learn the symmetry, right? It would be able to learn what symmetry means in this particular case, right? It wouldn't be able to... That's Chollets' point, is that a machine that's trained on thousands of examples like this one would sort of remember all the symmetries. It would learn what it means to solve this particular task, but it wouldn't learn what symmetry as a concept is. And a human innately knows what symmetry as a concept is. And if you are to solve this particular task from just these 3 examples, that sort of means that you also, it's almost a requirement that you understand what symmetry is, right? And this is the next sort of a criticism I have here, is that a lot of these tasks, I feel, they sort of test more whether a system has these priors than anything else. Because, right, he says, well, a system should have these priors already built in, and now we're going to test its generalization capability. But a lot of these tasks actually just, they sort of, it's more of a test of, do you have these priors built in? And then the second thing is, these things aren't procedurally generated, which is pretty cool, because that means, there's more diversity. there are probably smarter examples. Like when I saw each of these in the paper, I'm like, oh wow, of course that's also possible. And like, whoa, like you can never get that with procedural generation. But I feel it is going to be almost impossible to just reduce yourself to these priors that you explicitly list, because it's it's like, I think there are so many unspoken assumptions still in these tasks. He says you shouldn't do that. You shouldn't make a task where there are implicit assumptions. But I feel if he then goes ahead and by hand crafts these things, even if he really tries to not put any more assumptions in there, there are so many assumptions in there if you look at these tasks that are not listed.
I wonder how many priors there are, because it seems that if you're dealing with a two-dimensional grid, surely you could enumerate all of the possible priors in terms of symmetry and contiguity and so on. But this is quite interesting. So a person on Reddit came back to us and said that it's an interesting idea, but why not just use a different type of problem? So apparently there's Hofstadter's string analogy problem. So AAA is to BBB as CCC is to question mark. So the answer there is probably DDD, and then there's some more sophisticated versions of that. It seems to me that it's almost exactly the same type of system 2 reasoning required.
Yeah, I mean, for the first one, Cholet would say, no, that's not valid because you would need to know the ABC, and that's sort of world knowledge. Or you'd have to program this into the AI. And yeah, the second one, I agree, that's sort of the same, but that would not conform to the definition of these are like human scope tasks, maybe. Though a human can solve it. So yeah, I give him that. That's a pretty good analogy, honestly. It's just more flashy to do it in Cholet also, that's where these priors, these human priors come in. Because right here, what you're seeing when you look at this is like, the green thing going to the red thing. I mean, it's so weird. You immediately perceive the green thing like extending and going to the red thing. Crazy, right? So I don't think how you could map this efficiently into this string-based representation, except, maybe you have like 0, 0, 0, 0, 0, 0, and then like a 3, and over here a 5, and then 0, 0, 0, 0, and then the 3 like goes to the 5 or something like this, But then you would be back to these grids again, because essentially that's a grid. So I feel these string tasks, they also express the same logic, but they do not contain these fundamental priors. But then the question is it necessary that you have them in there for measuring intelligence? Who knows? Is it over? Competition?
Yeah,
Yes.
I think so.
Are the 200 secret test examples, are they now public?
I don't know.
Because I don't want them to be public. I want them to be forever hidden, because that, I don't know, but that's just going to be like fun for the future, because I haven't had my try at this yet. I find it pretty interesting because he himself, Cholet, goes and says, how would you solve something like this, right? In the paper, he has a section about what a solution might look like. And if you go to step 1 of that, it's like, build a domain-specific language to capture all of the possible tasks. And like, so it's like, create a programming language that creates programs whose outputs are these tasks. And then step 2 is like, use the programming language to match, like find the program in that programming language that outputs the examples that you see of the task. And to me, it's like, how do you solve AGI? Step 1, build AGI. Because if I had a DSL that sufficiently outputs these tasks and narrowly enough so that it doesn't output anything, like not a Turing machine, then I would have already solved AGI or at least I would have solved the ARC challenge. So how do you build ARC challenge? Solve ARC challenge.
Isn't that the same as him advocating to build an expert system, which is precisely what he said we shouldn't do at the beginning?
Maybe, it's like, build a DSL and then match the DSL, sort of, I guess.
Yeah, it's tough. I suppose it comes back to Minsky's 1968 definition of AI, which is that it's the science of making machines capable of performing tasks that would require intelligence if done by humans. And I think that's a completely meaningless statement, by the way. That's the problem with intelligence, is you just can't get a handle on it.
Exactly. That's right. That's what I've been saying. At the end of the day, here in Minsky's definition of intelligence, it contains intelligence, right? So, how much more washy can you be? And this, at the end of the day, you'll always be like, I don't know. I know when I see it, or something like this. It's like, and again,
but
we've come
but
back to
don't you
skill-based evaluation. That's what I said at the beginning. We're now at this ARC challenge, and again, it's a skill-based evaluation.
I think this is it. I think we're coming full circle, because we are now coming back to Minsky's view of artificial intelligence. So Minsky said the problem of intelligence would be solved if only we could encode human skills into formal rules and encode human knowledge into explicit databases. And that's exactly what we've just been talking about on this ARC challenge. We're talking about coming up with rules and knowledge to describe all of the things that you can do and all of the different types of symmetries and so on. Is that not exactly what Minsky said in 1960, whenever it was, long time ago?
It sounds awfully close, right? So I've had this idea about how to solve this. So hear me out on this one. You know, we've talked about GPT-3, and GPT-3 looks an awful lot like this. Like GPT-3 in context learning looks an awful lot like this thing right here. Like, you have 3 examples of a task, and you give me like the 4th one you need to solve. That looks like exactly what GPT-3 does, right? So it has never trained to translate, but it can translate due to this in-context learning. Now, it can do so because it has seen lots and lots and lots of variants of these things during training, but probably never exactly that. So my approach would be to build a giant training data set and then train something like GPT-3 on this to do exactly this kind of in-context learning. Now, how would I go about building this training data set? I would do sort of what Chollets says with his DSL. What I would do is I would look through all these priors, and for each one, I would write a function. So, for example, one of the functions could be produce a symmetry. And that function would take like a generic grid object, right? Put it in, and then it would output a symmetrized version of that object. Or like extend line would be a function, and that would take in something, it would just try to extend that. So if this is like a big thing and so on. So I would sort of, it's like reverse engineering the makers of the ARC challenge, but instead of what Cholet says, build a DSL that describes the problem, I would simply try to come up with a training data set that mixes and matches. And then I would just randomly apply these functions one after another. So one gives me first a symmetry, and then a line, and then a time, and then something going toward something. And the other one gives me, a bunch of other things. And you do some data augmentations where you swap all the colors and so on. And that training data set, I would then train GPT-3 on to do the in-context learning. That's how I would go solve this.
GPT-3 is like brute forcing this problem of multimodal outputs. It's like the zoo and saw could be gorilla, tiger, cat, I don't know. So it's brute forcing this multimodal output problem. But I think images is going to be too high dimensional for you to do that. You're going to need so all word tokens are like one dimensional, maybe like 1,000 length, right? So you're going to need to put all your images in that kind of dimensionality to brute force multimodal outputs.
Well, I'm not sure. I mean, I don't know. You could also just generate one pixel after another or something like this. And then it's just a sequence task.
I was thinking about them. But could I just articulate back to you? I'm interested to reason about how many possible priors could there be. Is it 10,000? Is it 100? But let's imagine that you came up with 100, and it was all of the usual suspects, like, contiguous lines and homogeneous shapes and all of that kind of stuff. And then you procedurally generated many instances of boards that had representations of these rules that you generated. So now what you've basically done is you've created an encoder that can represent any board configuration.
Yes.
And then you can use that representation and generate lots of maskings, and you can train it to fill in the mask. Is that kind of what you're saying?
No, I would. Well, the masking itself would be one of these functions that I train on. So if you ask how many priors are there, and then if we ask, okay, how many priors are there for human intelligence? Probably uncountably many, or at least in a way you could describe programmatically, you'd need uncountably many programs. However, you don't have to match the human priors. You have to think of what kind of priors did François Chollet think of when he constructed the ARC challenge? And that's a much smaller set. That's probably going to be in the order of 100. And you might go overboard a bit because you probably can come up with more. You rather oversample, right? So and that's why I think when someone solves this, when I let's say I solve this, and then I say, look, this is how I did it. I just constructed a big training data set out of these 100 custom functions I wrote, and I composed them in random order each time, and then I trained GPT-3 on it, and I, statistical inference in context learning output. Cool. That would be impressive, but the AI effect would kick in and say, wait, that's not intelligence. You simply coded these 100 functions.
Well, so the Kaggle challenge now, presumably it's all about diversity of tasks. So almost every single example you get is a novel task or a composition of these priors. So when you get evaluated, you'll be evaluated against lots of things that you've not seen before. But you're saying that it's somewhat predictable because it was all conceived by a few human beings.
Yes, exactly. And you only have to match that thought process. Or your thought process the thought process of these people has to be like in the convex hull of what you can come up with. And if you have the tight enough convex hull, you can replicate that.
Because you said the number of priors as conceived by François Chollet is very small. And I think that there will be a compositional relationship between them. So if you take all of the grids that are on the test set on Kaggle, and you write a domain-specific language to generate many permutations of these, there must be at least some transfer to the grids that you've not seen.
Yeah, I mean, the interesting thing here is the fact that humans can solve all of them, right? And they've tested this, and their result is a reasonably smart human can solve all of these tasks without problems, without instruction, right? And of course, any system you build is going to have some carrying over because you've thought of some of the things, right? But the interesting thing is humans can solve all of them. And that means one of two things. Either, one, you haven't sufficiently been able to encapsulate these core knowledge priors and the meta-learning procedure that leads to this. Or two, that in these tasks, there are actually more assumptions than are stated in the challenge implicitly. I don't know, but I'm going to count on a significant number being of the second sort.
It's really interesting because even now when we're talking about solving this, we are doing exactly what Chollet said we would do, which is to find a shortcut. But
yes.
if we did know about all of the priors, then it doesn't seem like it's even artificial intelligence anymore. It's something that you could just write using code.
That's my entire point. Because Chollet says you should explicitly list all of the priors that go into your intelligence test. And my point is, if you could explicitly list all the priors with sufficient detail such that you can make them formal, you would have already solved the problem. It's as hard as solving the problem.
Exactly.
I mean, that's my he might disagree and say, well, I only mean whatever is not the meta-learning prior, but then yeah, okay, but still, even that I could write down. Like if I could formally write down, because that's just a human prior as well.
I think these priors are like these discrete things, right? Like adding on data augmentation or something. It's like, how do you search for a prior?
This is the meta-learning thing. What we're talking about now is explicitly formalizing the priors, a bit like 20 years ago when we used to formalize knowledge in graphs. But you're saying, I want to look at this prima facie, so for the first time, and I want to discover what these priors are. I think Chollet is moving towards this program synthesis thing. So what Chollet wants to be able to do is go from this grid to this grid, but generate some code to do it.
Yeah,
right?
Imagine the code is like into a Python function, right? So it's a combination of A to Z at each of these slots. And we could do like an evolution search until we find this algorithm that does ARC, right? But it would take like all the computation in the world. But would that be intelligent? No.
Well, maybe it would. I mean, what if you could generate many permutations of code, and it would just be basic looping semantics that mutated things in the grid, and maybe you could model it as an agent moving around the grid, mutating cells that it was walking over or something. And you managed to, through this search space of possible bits of code, you managed to find a bit of code that would successfully mutate this cell into that cell.
Well, there's going to be, I mean, that's the exact difference to what you had on this DeepMind slide, right? Because there are going to be an infinite number of programs that conform to all of these examples, like infinitely many. I can always make a more complex program that also outputs these things, right? And even if you think like the simplest programs, there are going to be many of them that conform to that solution. I think this is what Chollet is trying to do, is he's trying to say, I am only going to consider solutions that humans can solve. And that's an entirely different thing, right? Because now, of course, when this green thing goes to the red thing, a human can solve that because, for whatever reason, we're like, oh yeah, going to something over, and these are the obstacles, of course. But if I tell you, no, actually, that's not it. The rule is actually the agent, you see, it always goes one diagonal and then one left. And then if the sum of the blue ones is 50, it turns this one green. And it just so happens to, in this grid, to make sense. I think, yeah, the focus of Chollet is whatever a human can do. Whereas I think what you had on the DeepMind slide is much more agnostic.
Well, that's right. But could we make a simpler version of humans? Humans have an unknown number of priors. Why don't we create a new measure of intelligence within a set of priors that are well defined? Why don't we create an ARC challenge which specifically only has, let's say, 2 priors, and let's solve that algorithmically, which should presumably be easy. Would that be a good place to start? We get from that to AGI.
I don't get how you would disentangle these priors, though.
Well, what if we said that let's make a new ARC challenge, but this time it's only going to have contiguous straight lines. So that means we can now write a solution to that using an expert system, right? We can say, given this grid, I'm just going to continue all of the lines in all the possible directions, maintaining the same color, and I'm going to select the one which produces one from the other, and I'll take the simplest solution, the simplest algorithm. So I've kind of solved intelligence in that truncated space.
Because you can write explicitly down what you're doing or how you're generating the environments, you have already solved the task. And that's my point. What Chollet, when he makes these examples, what he wants to do is he wants to say, okay, I'm going to make something that is only described by objectness and goal-orientedness. But then he doesn't formalize how he gets to the solution. He simply thinks, he sits there and he thinks, okay, I need something that's like object and goal-oriented. I can think of something. I can think of something, right? But in that process of generating it without, formally writing down, just derived from the assumptions, there are so many more assumptions in that. And I think that a significant number of these ARC tasks have these more unspoken, implicit assumptions about human knowledge that neither the maker of the problem realizes that they put in, and nor the test taker realizes that they use, because it's just so obvious to humans. This is just my opinion, right? But I feel there are so many of these probably in this stuff that this notion of make a DSL specific to these priors is probably not going to work. And that means that probably my approach is also not going to work. My approach would actually not be over these priors. My approach would just be to sit here and think like, if I were Cholet, what would I do? And that's probably going to be a solution that solves this thing ultimately.
Let's quickly come back to this hash table thing. Do you think it's hyperbolic to say that deep learning is like a hash table?
You're really scratched by this Reddit comment.
Well, can we let's look at this paper, right?
There are even papers about deep networks essentially being nearest neighbor searches in high dimensions. It's all a question of formalism, right?
So in this paper, Neural Arithmetic Logic Units, it made quite a surprising observation. I know we've spoken about this before, but it says that deep neural networks essentially can't extrapolate, not even on the scalar identity function. So the f of x equals x. So they trained it, I think, between a range of -5 and 5. And when they tested it outside of the training range, of course, it was different depending on the activation function. It couldn't extrapolate at all. So given that even in this case, it can't extrapolate on the scalar identity function, is it so hyperbolic to say what Cholet says, which is that deep learning algorithms are conceptually similar to a locally sensitive hashing function, which means they can interpolate between data points they've seen given a sufficiently dense sampling in the input space? I don't think it's that hyperbolic.
No, absolutely not. The question, I mean, anything is a hash lookup if you have the correct features. And except in these easy examples where you can actually write down the function, it's debatable whether or not humans would succeed so much better than deep neural networks.
With deep neural networks, I feel like it's almost like as if it's given the -20 to 20 range already. Like it's already got this massive thing that it doesn't even, I don't think it makes sense to try to see what happens outside of the bounds of it.
Well, that's a really interesting point, because it's like what we were saying with language, that we've got the convex hull of all of the different words, and someone on Reddit as well, on our Discord said, can you try and imagine a new color? And of course you can't, because we can only interpolate between red, green and blue. Or can you imagine a new word? No, we can't. We can only interpolate between the convex hull. So what you're saying, Connor, is that, even if I have a training set of all of these different images of dogs, for example, you can't really extrapolation would be, well, what's something that's not a dog? Well, of course, it's not going to help you with that.
Or what's something that's even more a dog than a dog? You can't generalize to new kinds of animals. You can say, yeah, okay, but that's an entirely different new direction in the manifold space, right? But in this case, we're talking about, can you extrapolate from what you know? And that would be something like, I'm going to give you the doggiest dog you've ever seen. Can you it's so doggy, it's not even close to these dogs. Can you classify that? And that's just not how data is in the real world.
But how can we contrast this conversation to what we were saying about ARC? Because it's not just the extrapolation, it's the information efficiency, right?
Well, in this ARC, I think it's about rule finding, right? Ultimately, this challenge is, if you see these 3 training examples, or actually if you see that number thing on the DeepMind slide, it's you to yourself think, what's the rule? That's what you think. There is an implicit assumption there that there is a rule, right? That's the implicit assumption. There is a rule. I need to find the rule. And the rule is going to be somewhat simple. in terms of the things that I know, and here is where the priors come in, right? Of terms of objects and movement and so on, but ultimately say, what's the rule? And I don't know if that has to do with extrapolation.
But there is a difference, though. When Cholet was talking about the levels of generalization, one of the things he said was tic-tac-toe, for example. It's not really a generalization because you can analytically enumerate all of the possible states. Similarly, on this ARC challenge, you can analytically enumerate a lot of rules and a lot of things that you can do. On a more sophisticated problem in the real world, if I come up with a rule of how I choose to go on the bus or how I choose to pick up something, that's huge. So any rule that I learn would need to be much more of a meta rule. It would need to generalize to more situations.
Yeah, exactly.
What if you have like a good representation of the tiles, and then like you have like angle of the vector that transitions from, like the labeled examples, you have 3 labels, right? So there's like angle of the vector that transitions each of them, and the meta learning rule maybe is like to use those angles in your representation space to infer this new transition, right?
Yeah.
Maybe to me it's a multimodal output problem, but I mean the representation, I have no idea how
but you're not going to have enough data to train something like this, right? That's the problem.
But I've been reading some papers on like transfer learning with GANS, where we're trying to like train on ImageNet and now use it for melanoma classification. It's like, what if you trained it on like a massive amount of these kind of like puzzles that could be similar-ish? Do you think that would be informative at all?
Yep.
It might be too abstract though.
That's exactly what I've proposed, right? Come up with a puzzle generator that you think closely matches what these people came up with when they created the tasks, and then train something on it. Yeah,
you would be cheating because you're what we need. I think the elephant in the room here is, in order to develop this kind of system too of intelligence, we need to have some kind of symbolic programming, right?
I've said at minute 1 of this conversation that I don't think solving the ARC challenge is going to result in intelligence. And exactly because of that, because the solution to it is just going to be reverse thinking of what the developers intended, and in my mind that's the only solution, because the number of implicit priors are still too many. So that's just my opinion on that particular thing. I think there are a lot of Reddit comments that are pretty interesting to this, no?
Yes,
don't read their usernames.
Let's start at the top. So we went out to Reddit and I kind of summarized Cholet's paper into about 20 bullet points. So the first thing we got was this. So the ARC challenge, this is from Shorten. In all honesty, the ARC challenge is a good throwback to traditional machine learning. Everything is getting cooked with deep learning soup without much transferable know-how. Heck, you can't even use language models in vision settings. Going back to some of his arguments, he echoes some others who rightly point out brain network are amorphous and denser without the need for BP. Oh, backpropaganda. The paper and the challenge attempted to nudge the community to think outside of the box.
Well, what's meant by traditional ML? Is it like linear regression? I mean, yes, you can apply linear regression to images and text. It's just not going to work.
Well, you've got that problem called the curse of dimensionality.
Yeah, okay. Yes, that's a good point. It's kind of bringing the community back, saying that instead of building more and more specialized solutions, you should maybe try to think of intelligence as a broader thing, like try to think of things that generally apply to data. But deep learning itself is a pretty general paradigm. Like, of course, we have CNNs for vision and transformers for text, but in general, it's like, let's mix linear algebra and nonlinearities and a bit of normalization and backprop, right? Gradient descent. Just the fact that for example, now called out this Flatland challenge, where it's about optimizing the Swiss railway network so it's a simulator of the Swiss railway network. And in the olden days, right, I would have actually had to understand something about the railway network to do this. But now my explicit goal is to understand as little as possible about trains, and it actually has a chance to work, right? By the way, anyone who is willing to participate in this, we're doing this completely in the open. Everyone's free to join in our efforts. But I now have a good chance of not having to learn something about trains or vehicle scheduling or whatnot because of deep learning, right? Similarly, I can build like a Go and a chess and a shogi bot. I have no clue of chess except for the rules, right? Because of deep learning, I can build like the best medical systems are built by people that have no clue of medicine. They don't know how lung cancer looks. They just know that some doctor said this is lung cancer, and they build. So I feel deep learning itself as a methodology is super general.
I mean, that was the amazing thing about deep learning, that in the olden days of classical machine learning, the data scientists were domain experts and would write very sophisticated feature extractors which did what you needed them to do. And now the incredible thing is we have this ubiquitous toolkit that we can just apply anywhere, but it only seems to work in certain situations because this person is saying that it's a throwback to traditional ML. I think it's a throwback to expert systems. You can't use traditional ML on the ARC challenge.
Well, yeah, you can't use expert systems except if you cheat and sort of think of what Cholet would have thought when he made the challenge, right?
Anyway, oppressor of virgins. And by the way, just before we get to oppressor on virgins, Yannic has set up a Discord server where he is running this Flatland challenge, and we're all on that Discord server. So feel free to join us, and you can talk to us at any time. But yeah, coming back to oppressor of virgins, said, don't forget to take a look at his Kaggle challenge. I like his fresh way of looking at things. The ARC challenge almost forces you to pinpoint the core of human intelligence. Indeed. Someone called Panties in My Arse says, what's the purpose of this YouTube channel? Does it have any particular goal? The world is awash with low quality ML content, and I feel this sub could use some assurance that this channel is actually worth paying attention to. No intention to disrespect. Just curious.
It's a fair question. We are mostly providing low quality ML content and have no particular goal. We don't even follow a consistent format, and the videos are too long. So yeah, there's no purpose to this.
Videos are too long. We haven't done a Siraj yet. We haven't set up what did he do? He set up some kind of, what was it, School of AI?
Yeah.
And started selling courses. We haven't done that yet.
It's in the making. It's just a matter of time before we rip you all off. And
We're going to rip you all off.
Send us your money right now so we don't even have to go through the trouble. Come on.
Yeah. He seems to give a pretty definitive stance on the nature versus nurture debate, and empiricist versus nativist debate. That the key to building general intelligence is to hardcode fundamental human priors. While I personally largely agree with this, I think there's a lot to debate with regard to how you decide what to hardcode versus what to learn. I wasn't able to find much discussion on this particular topic in the paper on my first skim, but I think this question is pretty central to the topics of this paper and should be a significant point of discussion.
Yes, that's the entire point here. Like, you hardcode some things, and the learning especially in the ARC challenge, the learning is almost non-existent, right? It's this rapid learning from these very few demonstrations. There is no notion. I almost feel like it's all encapsulated in one. Like, whether or not objectness is a learned property or a evolutionary built-in property makes no difference to the ARC challenge. And in fact, in the measure of intelligence, the formula, it's prior plus experience. Nowhere in the formula is the prior by itself or the experience by itself. So for the measure of intelligence, Cholet doesn't differentiate between whether you've acquired something through nature or through nurture. So I think for him it makes almost no difference at all. Even though I agree he does take like a pretty definite stance and saying basically these things are built in, but it wouldn't make a difference if they weren't, but if you just simply learned them as a child. Because in terms of the definition and in terms of the ARC challenge, you want to provide a system with these abilities beforehand.
What is quite interesting, though, is that the skill programs that these type of tests are looking for are innate or acquired within the first 18 months of our development. Many of the skill programs that we put into use every single day are learned, but we've learned them throughout our lifetime.
Yes.
Yeah, but in something like the ARC challenge, the goal is not to learn anything.
Well, the goal is to generalize rapidly from these few examples.
Yeah, I would say the goal is to apply some previous skill program that we've already learned.
Yes.
So he also says a very related story to the above is that of meta-learning. The idea of meta-learning, as I think of it, is that you learn an inductive bias that facilitates quick learning or good performance on a family of tasks rather than one task. This may be debatable, but one can say that this can allow the jump from local generalization to broad generalization. And then you get to the question of what is the best way to learn this inductive bias that accelerates your ability to learn these tasks. There's a kind of meta learning program associated with that. And things don't really stop there because you can have infinite levels of abstraction. I think a possible and very subtle implication is that the jump from broad generalization to extreme generalization implies collapsing across these levels of abstraction, which is something humans are able to do. Schumender discusses this collapsing concept in his 1987 thesis.
Schmidhuber. He's super famous.
Schmidhuber.
Oh, he's very... No, it's Schmidhuber.
Schmidhuber.
He's very particular about his name.
Yeah, is this... is that Mr. LSTM's?
Well, technically, Sepp
that guy.
Hofstadter is Mr. LSTM, but yes.
Yeah.
The Schmidhuber was his supervisor. I completely also agree with this point. If you think about meta learning or multitask learning, it's kind of washy how it's treated nowadays in deep learning, but the concept of it is sort of what we're looking for. Like what's a good algorithm that allows you to quickly learn from new data? The way it's framed right now is more of I give you many different tasks still in machine learning language where I have thousands of training examples. Whereas what Chollet and specifically, I'm really biased by this ARC challenge, but what he's looking for is more like I give you 3 examples, right? And I feel that's a different thing that the current meta learning community is addressing. Though I agree with the commenter entirely here that meta learning is essentially looking for something like this. And then I also agree that there's these levels, infinite levels of abstraction, and that somehow in these level, there is a recurrence somewhere. And that recurrence might be called intelligence. You remember when we talked about consciousness and Benjo said something like, consciousness has to do with attention. And I feel it's the same way there, that no. Humans can attend to their attention, and then they can attend to that, and so on. So it's sort of this recurrence relation among these abstraction levels that makes the intelligence or the consciousness. And I feel we're nowhere in machine learning to capture that.
Inductive prior that like fits the structure of meta learning. Like the original mammal paper, this inductive prior is that the initial parameters are like the thing we should share across the task. But then it could be like, I think the latest idea like metric learning is like we apply this data augmentation view to it, and that's how we apply the contrastive loss and like learn these object classes. Like this is a cat by cropping it and then comparing the two. And then I think another prior maybe is this idea of generative models that we've been trying to get after. And I think it's interesting though, like the structure of how are we going to share information across tasks? Pretty interesting.
Yeah, absolutely. And I think we quoted Christoph Koch, I think, on our consciousness Bengio one. You showed me the article, Connor, and he said exactly what Yannic just said, which is that, real consciousness should surely have this kind of recursive, reflexive, self-causal property. It shouldn't just be, just an end-to-end neural network. He also says, he or she, I don't know if it's... this discussion of intelligence is pretty human-centric, which seems intentional. However, I think many animals that we consider dumb are smart in their own way. For example, we think rodents are pretty dumb, but they're very smart at tasks that are ecologically valid to them. They are navigational geniuses, for instance, and I think this is also an important part of the discussion.
Well, I'm coming back to the contact lens thing one more time. It's like if you've seen Predator...
You're not going to let that one go.
Have you seen the movie Predator? How he sees an infrared...
Oh, yeah.
He's like the hunter and he sees them in infrared light, so it's like really easy to see them. So it's like if you can see an infrared light, you're going to be good at hunting, but you're not going to be able to do the ARC task, regardless of how well you can logically combine the things.
Oh, yeah, but the ARC challenge is very anthropocentric. Because if you think about it, the intelligence that we have is very much a function of the environment and how it can be expressed through acting in that environment. So to an alien, the ARC challenge would just be a complete nonsense.
Yeah, there's so many ways to perceive the environment. I think we have like the RGB filter on, or whatever the light spectrum is. I don't remember.
Yeah, again, it's exactly what Cholet says. With intelligence is in his mind with respect to a given scope, and if we think about building AGI, then we must give it a scope, and the scope that makes sense is the human scope.
But this is why I made the comment earlier that surely we should start by reducing the scope as much as possible and trying to solve intelligence in the most truncated scope and then build upwards from there to try and find the scope of human tasks.
The formal describing of the scope is that already the same complexity as solving intelligence given that scope, right? Because at some point from really simple to human, there's going to be a point where you can't describe it anymore formally, because you can describe the simple, you cannot describe the human scope. And I think at that point, that's the critical barrier there.
And just to unpack that a bit more, it's not just about describing. What if you could analytically enumerate all of the priors that humans have? What kind of compositional relationship would those priors have with each other, and could you describe that? Okay, so Zombie Coplip says, I should start with the caveat that I just skimmed the 64-page article, so my assessment is likely way off. So the McCorduck AI effect is probably the most relevant point here, and this is that every time we do something intelligent, people say, oh, that's not intelligent. AI research in the past has done a lot in the way of logical reasoning, but it turned out that it was easy to get a computer to be more logical than a human. So a good example for this is rule induction and inductive logic programming. So the recent research can be thought of as emulating what we'd call intuition in humans, which is actually hard for computers to do. As with humans, intuition doesn't generalize very easily, although the RANT paper seems to ignore transfer learning and meta learning. So he seems to be unhappy about that, he or she. It is true that few researchers try to achieve general artificial intelligence, though the author downplays some achievements. While AlphaGo was specific to Go, AlphaZero and MuZero are absolutely intelligent systems that work on more systems than a human could master. Core knowledge is normally known as an ontology and is an old concept, with Google Knowledge Graph probably being the largest one. With these nits out of the way, the authors assume that intelligence is a 1D scale of a system, which makes the system sound very dependent on the tasks presented to it. The authors assume that generalization is somehow more valuable than skill, The market tells us otherwise. Generalization has a pretty low return on investment. The authors admit that human perception of intelligence is very limited, but still abide by it. I think this is a red herring, which would enforce more human-like AI by sacrificing the advantages that AI already has over us with regard to logical thinking and the ability to ignore human priors. And yes, he says, I'm aware that most ML does not do this at all by using human-provided datasets. He finishes with, however, I do like the general point the paper is making. I would like to see more development in AGI, as for me, it's probably the coolest thing ever. I did love the discussion of Gödel, Escher and Bach, which is a book that was written, I think, in the late 1970s. I'm a bit disappointed that they explicitly want a human-centric approach, and I think they don't seem to appreciate the work on AGI very much, even though they're proposing it.
I mean, this, okay, to the second point specifically, the authors assume that generalization is somewhat more valuable than skill. The market tells us otherwise. How expensive is the source code of AlphaGo? And then ask yourself, how expensive is the team that built AlphaGo? So I disagree that skill is valued by the market. It's maybe particular specific skill, but I think the return on investment on generalization is very high. And also, I mean, the commenter here is absolutely correct. Chollets does focus on generalization, but that's Chollets' choice, right? He simply says, I define intelligence as the generalization difficulty over a scope of tasks, which is to the first point. I mean, the author here is correct, but that's the choice Chollets makes, and he argues it well. And what I find most interesting is that's like the very first sentence that you said, Connor. mu0 are absolutely intelligent systems that work on more systems than a human could master. Do you have like a more elaborate take on that?
Well, I think we're still on this idea of like, well, model-based reinforcement learning, you learn a model and then you learn it in a latent space so that it's computationally tractable. I mean, at least for robotics is what I opened up with, just thinking that like mu0 could work for robotics. And it seems like Dreamer is a good example of this, like the Planet paper. It's the same idea of like, let's learn a latent space world model and then plan in it.
Could you articulate what's different about mu0 and AlphaZero compared to AlphaGo?
Well, I think what is so different is that in the latent model, when you do like a transition, if you know the chess, like if you have the chessboard, you know if you move your castle, you know what happens next. Whereas with mu0, they're going to use the compressed latent space and not use like the simulator, the ground truth transition. So like state action, next state transitions. If you use that ground truth lookup, that makes the problem like so much easier compared to learning those transitions.
Okay, and with AlphaZero, I think the point is it wasn't given. It doesn't know the rules of the game. It wasn't given examples of actual games played by humans. It just starts from nothing. It learns the rules of the game from the simulator. So it could potentially you could feed in chess, for example, a chess simulator, and it would learn it exactly the same. It doesn't care that it's Go as long as it's an adversarial two-dimensional board game.
Using that ground truth chessboard to do the Monte Carlo tree search. So that's what AlphaZero is like, not general because of that, I guess.
Yeah, exactly. There's an interaction between the simulator and the learnable part, because at every point in the Monte Carlo tree search in AlphaGo or AlphaZero, you use the simulator to tell you which actions are legal. So it's not necessarily it learns the rule of the game as the rules, but you're right in that it learns how to play the game in a way, right? It learns the good strategies of the game without ever having seen humans play. And then mu0 doesn't even have the simulator at hand. It needs to kind of come up with its own thing. And I agree with the commenter here that I think something like mu0 is an extremely important building block that we have in our disposal. I feel it's still not fully enough, because in mu0 you still do this exploration by simply basically by randomness. So you have like some exploration constant in there where every now and then you try something new. Whereas I think what humans do is they have a model of the world and then they deliberately explore certain parts. They deliberately form hypotheses of spaces they don't know yet, and they deliberately try to explore those spaces. And that's maybe something more like the Dreamer or things like this, or like when we discussed with Hari, when he says you have like an explicit exploration component in a model. So I feel it's not all the way there, but I think something like mu0, where you learn a model of the world and you use that model to plan ahead. I feel that's a giant thing. And honestly, I think that is innately connected to your ability to navigate in 2 and 3D. In my mind, whenever I plan in my head, it's almost like you're navigating some landscape, right? It's the same terminology, like, oh, I can get from there to there, and then I can get from there to there. Like this planning, logic, and navigation all seems to be the same component in your brain. And I feel that AI systems might want to use that fact. Navigation, planning, logic, all the same.
Would you use any of those things when you were solving the ARC challenge? Would you use your imagination?
I don't. Probably not. I'm probably never going to start because it's just it's a big task.
Well, remember we had a discussion the other week, Yannic, where you said that you could verbalize what was going on in your System 1.
If I had enough time, yes.
Coming back to the Reddit thing, one thing he or she said was that generalization has a pretty low return on investment. And I would argue that, because I think the person is implying that we don't have generalization because clearly if it had value, we would have done it. But I think we haven't done it because we can't do it. And if we could do it, it would have even more value.
Yeah, just look at for how much IBM sold. What was their thing that won Jeopardy? Watson. Like that thing was entirely useless, right? It could not generalize at all, but they made like this huge business case out of it, and people were throwing money at it until they realized they couldn't do anything. But the promise was basically generalization. The promise of Watson was you know this thing, you can just feed in all of your company documents and it magic, right? Like triple your returns and stuff. And people were paying for it until actually they realized it doesn't do that. So I think it's more along the lines of what you're saying, in that it has value, we just haven't done it yet.
Also, just local generalization is like being able to ask the question in a slightly different way. Like this idea that you can search through your company documents with natural questions is like this local generalization means you get to ask it in a non-perfect way.
Yeah. Yeah, but already that was so valuable, right?
Right.
So Hybrid RXN says, disclaimer, I skimmed the paper and still have to read it in full. I mean, to be honest, it's a monster of a paper. It's one of the most dense, scary papers. The thing is, it's not like it's difficult to understand, but there's just so much information packed in there. I've personally been trying to make a video about this Chollet paper for about the last 2 months. And it's one of those things that if you don't deconstruct it into very small, manageable chunks, even Lightspeed Yannic Kilcher, and this is a guy who can deconstruct and consolidate a paper in his mind and just off the cuff do an entire thing on it. Even Yannic had to break it down into a 3-part series and capture bullet points about it. So it's probably the only paper which has defeated Yannic. But anyway, the AIC competition was short, and no new model seemed dominant, and arguably enforced trial and error brute force search. So what did we learn from the AIC challenge? Do you want to
I guess that we are not able to do these kinds of things yet. I mean, the entire point of ARC is that a human can do it. Like almost any human can do it, right? That's the entire point, and machines can't. I think that's the simply pointing this out there. Hey, there is this task right here, and it's so easy that any human is able to do almost perfectly well on it. but the machines just suck. We've sort of in the last few years, we've maybe gotten a little cocky in that we think, with deep learning and all, we're challenging the humans on pretty much all fronts. But this shows that something like uber simple is still out of reach.
Yeah, well, the person then goes on to say, what groups or research labs are seriously engaging with the ARC dataset? Why not? No one's engaging with it. Chollet's point is that we are barking up the wrong tree with these skill-based AlphaGo type systems.
Are there any big names on the leaderboards? I don't know.
Should we have a look? IceCuber is in first position.
Nice. Good job, IceCuber. Well, for real, I mean, if there seem to be lots of people. Of course, the question is, how good is 0.79? I have no idea.
I think if you go to the notebooks, you can get a good sense of what they've done.
So cellular automata. So this has been upvoted 428 times. So this appears to be where the center of gravity is, shall we say?
Here is a video of a cellular automata colorizing the bars in the order of their size. Okay. Nice.
Okay.
And it's a wall of text.
It's a wall of text. Well, this is quite cool.
So, okay, I guess we know about cellular automata, but to make them into a language of reasoning, that seems pretty cool. So I'll check this out after this is over, definitely.
So domain-specific languages and genetic algorithms. Decision trees for ARC, I would imagine they didn't get much traction. A basic CNN approach. Honestly, it looks like people are just scratching around here. I mean,
we're waiting for the AlexNet moment of ARC.
Yeah, I think it's fair to say that is not going to work out very well for those folks.
So I guess no serious lab is involved in this. Is the answer?
That is the answer. So we can just finish on hybrid RxN. It seems like there are two philosophies to better generalization. So scale up GPT on the pre-train, then transfer or develop better inductive biases, so graph neural networks or tree LSTMs, program synthesis, search methods, etc. Might have missed in this paper. But curious to hear a modern take on what Chollet thinks of feasibility and trade-offs of existing approaches, especially with new advances, so big transfer, GPT-3, plan to explore. If the goal is task-agnostic generalization, given the results from the challenge, for instance, it seems like self-supervised learning is here to stay, computer vision, RL, and NLP.
Yeah, I think it's back to it's going to be way easier to scale up GPT-3 than it is to find more inductive biases. That's my take.
Yeah, probably. But I guess the question then becomes, what do you scale it up on? The point of ARC is that you don't have a data set, right?
Do you guys know about program synthesis?
This AutoML 0 comes closest to what we know. I know very little. Yeah.
Well, back really quickly, back on this idea of building a generative model from only 3 examples. Maybe it's back to our idea of like the curriculum learning poet stepping stone kind of idea, where like once we learn to generate from like maybe the idea of learning to build a generative model from like 3 examples is a process of going from like separate, like with CFAR 10 with 50,000 examples, we can easily build a generative model. It's still much higher resolution than the ARC is, but it's like, so maybe it's like the stepping stones that you got to go from generating this distribution, now go generate this distribution.
Right. Because the problem here is as well, it's not like the even though the grids are relatively small, the set of grids that conceivably appear in these tasks is so tiny and so specific to humans, right? It's so human specific. It's not like you can write down how to get there. And then if you do something like Poet, I mean, you know that the issue with Poet is you never know where it ends up. And it's for sure not going to end up at a human specific thing, right? So That, yeah.
I'm trying to compare like the really complex terrain it walks on to
Yeah.
generating the ARC corpus. It's like, how would you connect like being able to generate an Atari game to the proc gen benchmark, where because the Atari to Atari game has a lot more variance than the proc gen, where they still have this kind of underlying distribution, but then there are these rules that are causing it to be like a different orientation of the maze. It's like, imagine going from you can generate proc gen levels to generate a new Atari game, and then all these different things you can generate to get to ARC.
The thing with the proc gen is that there is an underlying rule, right? There is a and it's simple enough such that a human had to sit down and program it, right? If you think about generate a new Atari game, not like a new version of Pac-Man, that you can do, but a new Atari game, a 58th Atari game, there is no rule that you could feasibly write down in less than 10,000 pages that describes how humans went about constructing the first 57 Atari games, right? That's simply, that's what I'm, that's my like current point from earlier. If you could write that down, you'd have already solved the task, right? The entire thing about prog-gen, I feel, is to reverse engineer the rule. If you wanted to, not if you wanted to solve, but if you wanted to construct these environments, to reverse engineer the rule that makes these environments.
Well, I think they're all trying to reverse engineer like what's generating the data, right? And it's just, but like even if they can't write it down, they're storing it implicitly in the parameters.
Yes, but the hardness of being able to learn such a thing is probably as hard as to write down the rule that generates it. Maybe.
But then I'm thinking about like these high dimensional spaces, and that's the whole problem behind writing it down, right? Is the fact that it's these high,
Well, it's not high dimensional. If it can be high dimensional if it was generated by a simple rule, then it can be as high dimensional as you want, right? But the fact is, we don't know. If you can tell me the rule how the humans made these Atari games and why they made these 57 Atari games, right, and not other Atari games, and how they decided on these 57. If you can write down that rule, I can easily make a generator that generates a 58th. But you can't.
Right. But so I guess my question is, can you learn that rule from the data?
Hi. Yeah, and I'm guess you can't if you just have 57 training samples. With current methods, you probably can't.
So is it an issue of model capacity, or is it an issue of we need 2,000 Atari games?
I don't know. Yeah, that's a complicated question. I have no idea. I don't know. I mean, if we come back full loop to Chollets would say either you build in better priors, meaning that you have a better idea of what the rule of generation is, or you give more experience, meaning you have more data points. You can achieve both ways.
Right. So I like thinking about this object permanence prior as being stored in the parameters of the neural network, because then it's easier to transfer it. But I definitely like these generative models, like this idea, like GameGAN is really exciting. The idea that you could put like the OpenAI gym suite into generative models. Like I don't know exactly how many tasks are in the OpenAI gym benchmark, but like, could you put all of those tasks into a single generative model and then just condition them with like a normalization layer to produce a different, like, condition it so now it puts out car pole balancing, and condition it so it comes out bipedal walking?
I have no idea. I haven't read the GameGAN paper, so
yeah, I'd imagine it's like a capacity issue though. Like, I think GameGAN, if it just scaled it up, could easily put the Pac-Man game in there by memorizing it.
Oh well, yeah, by memorize, but you'd want something that like generalizes and whatnot.
I feel like the generalization is just the product of like a ton of regularization. Like, if we drop out paths like crazy and then we augment the data, it's like, that's to me where the generalization comes from.
It's conceivable. I mean, that would amount to the priors you build in, right? That you say, okay, dropout is a form of a prior.
Mm-hmm.
What are your final takes on Chollets?
I think it's a noble attempt at defining intelligence and making an intelligence benchmark. I think that in some ways this attempt has failed because we're not smarter after this. And intelligence remains something where the only way to define it is I know when I see it. It just remains, or because either you can't measure the quantities that he's proposing, or if you go to something like the ARC challenge, I seriously doubt that, for example, he has listed all of the priors that go into it. And I seriously doubt that when the ARC challenge is solved, that anyone would be convinced that this has anything to do with intelligence. And I think it will remain the I know it when I see it. And lastly, I think this criticism of deep learning as, or generally machine learning as, oh, it's just skill and it's not real intelligence. It's true, but I think it's the wrong way of thinking, sort of the wrong way of thinking about it, in that I think something like AlphaGo is incredibly smart if you factor in the people. And I don't mean this in the way that Chollets says, well, it's just a people program. No, I mean the symbiosis, the generalization capability of the DeepMind team plus the computers they have is immense. Yeah, that's
I see. So you're saying that we should see them as one whole.
Yeah, I think that process, in terms of generalization capability, if we're looking at that symbiosis is one of the most generalization capable that we have. And you can't go measure this with any kind of psychometrics or anything.
So do you think at university they should teach Hutter and Legg's definition of intelligence, or Chollet's?
Well, probably neither. I like this paper a lot, but I think for any practical purposes, it's like a nice academic exercise. But I doubt this has any consequential, not even practical applications, but I doubt this has any consequences at all.
Well, I like this function of like priors, experience, generalization, difficulty. I think that is a useful way of thinking about any of these problems.
I mean, personally, I love his formalism. It makes perfect sense to me. And it's almost as if he's trying to be a contrarian, like saying the emperor's got no clothes, right? He's saying that all of these folks are working on AI systems that are not really intelligent. I think if that was his aim, I think it's been a success.
As a fellow contrarian, I absolutely respect the attempt to be a contrarian.
My one issue is with like, I think the super glue benchmark is pretty good, even though you know the structure of the task. And I don't understand why he likes the animal AI Olympics more so than super glue, but just because you know all the tasks beforehand, I don't know. But I like super glue. Comparing it, he says like super glue is awful and animal AI Olympics is awesome. And I don't know if I think about that. I kind of like it.
Yeah, and similarly, all of these things. Similarly, Coffee Cup is awesome, while AlphaGo is not awesome. I see no difference.
Do you guys think that we are fundamentally going in the right direction on AI research? I'm quite cynical, like Chollet. I think that in many ways we're wasting our time.
Are you thinking about in-context learning with GPT-3 now?
Well, it's a similar thing. It's actually analogous to what Chollet is saying about deep learning being glorified hash tables. GPT-3 is a very, very clever hash table interpolation machine. Mm-hmm. I don't think it's cynical because it's incredibly useful. The utility of this is incredible. It's almost like a new type of database. Only you can query it using natural language and it can reconstruct whatever you need it to. It's very powerful, but is it intelligent?
Well, but rather than asking that, I would say humans, as a result of developing the kind of AI that we're developing, have gotten so much smarter. I have a phone, and with the phone, I am 100 times smarter than without the phone, right? So I'm not more intelligent than before. The phone, apparently, according to all of these definitions, isn't intelligent by itself, but with the phone, I can outsmart anyone. So I think we're very much going into the correct actually even a better direction than AGI, because AGI is like going to singularity and we're becoming obsolete. The way we're developing AI is that we make ourselves so much smarter.
That's super interesting, because in philosophy, that's known as the extended mind. So your phone and the internet is an extension to your mind, and you can access this wealth of information. But if you think about the growth of capability, it must be limited. So now you have all of this information at your fingertips, all of the information the world has ever known. And what it does is it makes you more efficient at achieving certain things in certain situations. But
yes,
as you improve that
faster.
but as you improve that efficiency, it kind of levels off, doesn't it?
Well, I'm not sure we're anywhere close to the end. Like Elon Musk would say, the bandwidth between you and the knowledge of the world is limited by 2 thumbs. And that's a pretty big bottleneck right there that we can still lift.
That's it, because GPT-3, I think, is the pinnacle of information efficiency through text. When we have something like a neural interface, I take your point that we might, as a civilization, take our capability to the next level. But for now, the limitation is something like GPT-3. GPT-3 allows us to ask any question and almost immediately search all the information in existence and get the answer.
We have like a 200,000 GPU cluster. But,
Yes.
How long can I ask Google, has anyone tried data augmentation on the discriminator in GAN training? Questions like this. Asking questions like that, I would be able to iterate on my research ideas a lot faster. So I think if it can generalize to these kinds of questions, has anyone done neural architecture search on normalization layers? If you can ask it that kind of question, right?
Yeah, well, that's really interesting, because what we're saying here is, as individuals and as collectives, we iterate. There's a lot of redundancy, and the iteration cycles are quite long because we have to do research and we have to find information and so on. And those iteration cycles will be getting more and more efficient. The velocity will increase. I guess I'm asking, there must be some limit to this. So with technology, we will increase our velocity to a certain point.
Limited power.
And when the velocity is going at maximum, is going as fast as we can, will we reach some kind of escape velocity? Will we develop some kind of super artificial intelligence, or will we develop some kind of technology that catapults us into the future, or will we saturate what we can discover?
Yeah, good question. But I don't know. I don't want to speculate. The optimist in me says, at least for now, we can accelerate quite a bit. And that's going to be my lifetime, and it's going to be fun.
Well, I think Chollets would say that you're already going at light speed, Yannic, so you personally couldn't accelerate any faster. Honestly, I've really struggled with this. I've been reading this paper for a long time. It's dense. There's a lot of stuff in there. I'm going back and forth because it really resonates with me what Chollets is saying. I think he's one of the best critics of deep learning. In his book, Deep Learning with Python, there's a whole chapter in there on the limitations of deep learning. And many years ago, he articulated a lot of this stuff. And of course, he's developed it further since then. But I don't think he's saying that there isn't utility to deep learning. I think he's just saying that a lot of people don't understand its limitations.
That means we can sell it much more effectively.
Exactly. Anyway, on that bombshell, it's been emotional. It's been great. We'll see you next week.
Thank you.
See you, folks. Remember to like, comment, and subscribe. We love reading your comments.